There we go. All right. Cool. Look at those good-looking guys up on
I'm in the conference. I can't do this.
All right. So welcome back from the poster session, everyone. Super happy to see you all here. My name is George Cantor. I'm from Carnegie Mellon University, and I'm going to be moderating this session. So I just want to explain a little bit about how it's going to work. We have these three esteemed researchers who are all doing technology and forestry, and they have slightly different takes on it, and we're going to hear from them. They'll introduce themselves in a second. I've got a list of questions prepared to ask them that hopefully will, are interesting, intriguing questions. But the very best outcome here is that I ask the first question, and then this all just turns into a free-for-all. So if you have questions that you'd like to bring in, please step up to the microphone and ask your questions. If you'd like to respond to the conversation that goes on, as the conversation is happening, put your hand up or step up to the mic, and we'll bring you into it. This is this forestry robotics is a relatively new thing. We're bringing this together here, and we just want to get to know each other. All right. So that said, I'll hand it over to Mikhail first. Can you introduce yourself? Say a little bit about.
Sure thing. So hi everyone. So my name is Mikhail Classeiro. I am the CEO of IFRRIA. It's a company from Portugal. We've been dealing with mobile robotics in general, field robotics more recently, forestry robotics even more recently. We started around 2017 in forestry robotics specifically. I would say that among all the projects that we have going on at the company right now, it will be the lowest TRL project that we have because of the many challenges that you've been seeing in the morning and the many others that we're going to be discussing now in this session and in the afternoon. And thank you for organizing this, George and Francisco. Great job, by the way. We deal with the overall ecosystem development of mobile robotics, like from firmware, low-level development, and then kinematics control, and then localization, path planning, navigation, decision-making, a little bit of perception as well. And we have a project going on called Safe Forest. Part of the works that have been presented in the morning are related, and some in the afternoon, and some of the posters as well are related with this project. So it's a project that involves my company as coordinator, and then Institute of Systems and Robotics from University of Coimbra, ADAI, represented here by Carlos as well, and of course CMU. We are trying to develop a multi-robot system for fuel management, also a topic that was discussed in the morning by David. So the idea is to reduce fuel accumulation so that we can reduce the incidence of wildfires and the consequences inherent to that. So yeah, I'm very excited for this discussion. Thank you.
Thank you. Philippe?
Yes, my name is Philippe Giguère. I'm a professor at Laval University in Quebec City. So I do computer science, but I mostly do field robotics. I'm interested in perception, 2D, 3D. And I'm a part of a research consortium called FORAC, from the Forest to the Customer, FORAC. And they're the one who kind of interested me into forestry problems because they're scientifically difficult, it's challenging, but also there's this funding available, but also it's from a society point of view, these are important problems that we need to solve. And within our research lab, the NOR lab, we try to do field robotics in extreme environments, snow, forest. So, forestry, again, as I said, is very challenging. So that's why I've entered the field for about months.
Yep. I think Owl liked that. I'm Peter. It's a pleasure. First of all, I want to say thanks a lot for throwing this workshop. I've been geeking out all morning. It's like the work that's being presented is so cool and very relevant for what we're trying to find with Gaia. So my background is largely, I was a robotics perception engineer in the autonomous vehicle space. I started at Ford and then went to Argo AI and then Main Mobility. Big company to smaller and smaller and keep going smaller. Really loved the work, and this kind of bleeds into why I'm here today and what we're up to with Gaia. I loved the technology for the sake of the technology, right? I was at IFRRIA 3 years ago, and then just again geeking out the whole time. But like, it's insane what this kind of stuff can do in the world, right? I always frame it as, forgive me for a sec, it's going to be cheesy. I always frame it as robotics and AI. I see it as the digital revolution of the last century finally becoming physically manifest in the world. We're no longer talking about bits and bytes and pixels, right? When you frame it with that step back and you frame it in that very melodramatic way, your imagination really runs wild with what kind of positive damage this stuff can do in the world. But in the space that I was at, this might be a hot take at ICRRIA, again, forgive me. But when I stared at it, the great majority of what's happening as far as capital and talent is getting applied to minimizing Uber's unit economics. And I was not convinced that that was the most meaningful application for this kind of technology in the world during the time and day that we live. We have some immense problems. And so really Gaia is our best attempt at how do we aim this awesome weapon at one of our biggest problems, climate change. And so with that, we're a very perception heavy company. We're aiming to apply a lot of these kinds of perception AI that we're familiar with from the autonomous vehicle space towards verifying forest-based carbon credits and starting to make this whole solution a lot more viable and economical to make trees a viable solution for carbon sequestration. Excited to be here.
Great, thanks. Yeah, so actually your introduction leads great into the first question. You know, the gorilla in the room right now in the autonomy world is the self-driving car industry. So obviously there are people spending billions of dollars on bringing these technologies into reality. What kind of lessons can we learn from that in forestry? What kinds of ideas port over? What kinds of things are bad ideas to try to port over? I'll address this to Peter, but you know, I'd like to hear what everyone thinks about this.
Oh God, okay. Where do we start? So first of all, I do want to caveat this with some clear bias, right? I'm a perception engineer, and Gaia is a largely perception heavy company. And so that's a lot of the lens that I look at, but there are reasons to this, and I'm happy to kind of touch on why we have such a perception heavy approach to these problems. But before I get into that, two things that we can carry over from autonomous vehicles. One is just a very general kind of structure of how to solve these problems, right? And so we know things. We know ransack, we know occupancy grids, we know neural nets, we know how to build up a tech stack such that the brilliant and awesome robotics engineers who build these stacks can actually do so, right? Working largely off of logs and automating a lot of this workflow. And so that is something that we very, very much so can carry over, right? We know how to build stacks, and the general structure of that stack is important. I tried to be too clever over the summer, and the only engineer on the team was me, the only robotics engineer. And I tried to not even solve for odometry. And my advisor, Tom Voorhees, was yelling at me, no, you kind of need odometry. You know, so point being, we know how to build these stacks, and there's a way to do it. The other thing that I think should really get carried over is this understanding of the current advances in hardware, right? This is this whole other half of what we're talking about here. Again, it's not bits and bytes. There's a hardware piece to this. When you talk in forestry, I talked with, I'm going to be very blunt. You know, when I talked to a company that is an exact expert in the space of forestry and with specifically applying LiDAR to it and to do these inventories, he told me, you know, Peter, I really think a whole lot's going to get unlocked when LiDAR gets below, let's say, the $20,000 price point. And I didn't say anything on the call because I'm thinking maybe this is some sort of weird edge, but it's there, you know, like the no one in this space is looking at what's happening in autonomous vehicles and in automotive. The price curve of that kind of tech is plummeted. You know, we can buy one for $10,000, $20,000 today. That's pretty good. And so honestly, bringing over a lot of this kind of insights and the hardware tech that's evolved for and gone already down this price curve is a big deal to take over. One thing I want to say on here is, well, two things to kind of like look out for. First of all, there's something called a route network at pretty much every autonomous vehicle company, right? And then what that means, they all have a different word for it, right? I learned that very quickly. It was very confusing, but they always have some sort of semantic map that they're all manually encoding. Actually, when I was at ICRRIA 3 years ago, one of the more interesting talks was the lab up in Toronto from Uber trying to automate and machine learn to automate that map. But the whole point of this is that there's always some sort of fine tuning and wrangling these systems. This is where the state of the art is at, right? There is a lot more about RL and all these really cool things. It's not there yet. And so all these systems are really fine tuned to their applications right now. And so there's a lot of that we have to do here, right? When we apply these systems, the domain is very different. There's beautiful vertical structure, which as a perception engineer, if you're trying to solve a SLAM problem, it's so nice, you know, but it's a very homogeneous kind of environment. There's no iconic building that, oh yeah, every time we pass that building, we get such a nice snap, you know, like we know exactly where we are. It's up, tree. That one's a little bigger, that one's a little smaller, you know, so it's a very different domain, very noisy, and the noise is very different. The foliage, this was touched on earlier today, right? And the last thing I want to say here that we have to be careful of that carries over is this 1% problem in robotics, right? And so if people talk about why are autonomous vehicles not out there today, they always bring up 1%. So it's a specific domain where the system needs to be perfect. If it's not, if it fails in that 1%, well, someone died, right? And so not great. Here, honestly, probably no one's going to die, especially with the way that we're deploying these systems. Maybe your system runs into a tree or something, but there aren't too many kids with a soccer ball rolling, into the forest for you to run over. But that being said, there's a lesson to be learned there, right? Of let's try to find the easier applications to deploy where we can offer immense value without having to have the system be absolutely perfect. And I was just talking with Professor Cantor about this earlier, and I agree. It's a lesson that is often slow learned among people pushing out technology, and something that we can get a lot out of that space with. I have a lot more to talk on, but I've been talking for a minute, so let me catch my breath and give the others an opportunity.
So yeah, I think now that while we're in the sensor bandwagon, I think something very important with doing robotics in forestry is to understand how these machines operate and actually watch them in operation. We're lucky we went to a school where they train people. Ina Shafizat Miguel, she's also doing work in forestry robotics, and we saw these machines being operated live. And it's like the harvester, it's called a feather buncher, where it grabs a tree and cuts them, and it's like the third tree that they cut snaps in half, crashes in the cabin. Okay. So basically, is when you do robotics, imagine your robot, take a 30-foot long baseball bat and hit your robot all the time. And now think about where would you place your sensors in the self-driving car? On the top, on the roof, on the sides, they're all gone. Okay. You tell us, here's our machine. Wherever you see bare steel, don't put sensors. They'll be knocked off. The part is being rubbed constantly. So we have to think about differently about where we place our sensors. And I think also maybe we need to think about a different paradigm, such as sensors as a consumable. It's easy to destroy one camera, but if I put 30 cameras, I'm guaranteed that one will work, right? And all you do is, after so many hours of operation, you go and replace the cameras that have been broken. Cameras are like $5 now for cell phones. Of course, that means now we have to have stuff for auto calibration, anomaly detection, but that's the kind of thing that traditionally the sensors were expensive, so we're super paranoid about losing our sensors. But like I said, how about they're just consumables that we replace all the time? Same thing, optics. Cameras are great, but then the optics might get dirty. And one thing that we learn is every time the person leaves the machine, the harvesters, it's a liability. Their fingers might get crushed by the doors, they might fall on the ground, they're alone in the forest, they might die. So then they would try to minimize the number of times these people leave the machine. Same thing, if you put sensors on the harvesting head, people have been killed getting close to this harvesting head because they have fingers that will crush you, or they have a circular saw, which is about this big, that has inertia for about 2 minutes. So it's very, very dangerous. So they don't want to touch things. So I think that's one of the things which is different about forestry is they're very, very dangerous machines, and they operate in very difficult conditions, which is not what we have in self-driving cars.
Okay, so my 5 cents to this discussion, and I agree completely that there are differences in perception, and I could perception and safety, and I could wrap it up that by saying that the standards are completely different. So we need to define specific standards for forestry robotics to start with, and this would require a whole workshop only dedicated to that. So that's a tip for those organizing this workshop for next year, maybe. I would just like to say that besides the fact that we need entirely different standards, we also need to realize that the whole architecture is very different. I mean, intelligent transportation systems are more on the single robot side, even though they can benefit from other robots around, other vehicles in this case around, and other IoT and whatever. And my belief is that forestry robotics is 100% about multi-robot systems. So what I mean is that people are focusing in single robot, which is normal because there are plenty of challenges to deal with. But the truth is that one single robot will not make a difference in the end, right? I mean, 30% of our planet is forest. Only in Portugal, 40% is forest. So having a robot with a team of humans around will not make a difference. We need many, many robots, which means that the level of collaboration, of cooperation system that we need to deal with is entirely different, the architecture itself, from intelligent transportation systems. So yeah, there are a lot to learn at the individual single robot level. But at the multi-robot level, I think we're going to need to look somewhere else or create our own architecture from scratch, basically.
All right. You have a question? Yeah, come on up. Perfect.
How do you look at kind of tree harvesting and harvesting of forests versus fire management of maybe national parks or national forests?
If I could start, I think first is the size of the machine. Harvesting trees is the machine need to be bigger, and also they're able to make way to get to the tree they want. Like we have dash cams installed in harvesters, and we could watch like hundreds of hours. And for instance, if the trees are too small, they just rip them off the ground. You'll tell me it's terrible, but it's because if you know the ecosystems, you know that if you leave a single tree with a very small topsoil, because it's the Canadian Shield, first storm was going to happen is that all the trees are going to be toppled over. So they have to remove everything because it's going to be destroyed anyway by the wind. So these machines are able to literally engineer the environments to get to the tree they want. As opposed to when you do the fuel management, machines are smaller and they're not going to go and cut trees to make way for themselves. So I think that might be one of the big differences.
When I hear this question, like honestly, my biggest point that my mind goes to is really just one is very heavily an actuation problem. The other is very heavily a perception problem, right? And so like you're fixating your sensors onto something for the forest fire management. That something is probably cute from a robotics perspective, right? It's like a drone with DJI GPS navigation, like it's very solved, very manageable, as opposed to, but the perception problem is hard, right? Is how do you actually, get that detection with a low false negative, false positive? But then the other is just the actuation, as though like ETH Zurich was presenting right on and saying, oh, the perception, we did something basic for the tree detector. And really a lot of the problem is the navigation.
I don't have nothing to add. I think they already covered it.
All right. Yeah, so again, I'll encourage the audience to ask questions anytime you feel like you just walk up to the mic. Do you have one? Yeah.
Can we just ask questions on things that have been said or?
Sure.
So sorry, I didn't get your name, the person from.
Mikhail.
Yeah, so you mentioned something, well, you were talking about multi-robot coordination. So can you maybe expand on this, the multi-robots? Well, where do you see this? Because I know in Canada, in the timber harvesting side of things, it's usually one operator operating the machine. They have a block of forest that they're trying to cut, and then there's another machine that will follow to remove the logs or remove the
Exactly.
trees. But there's no multitudes of robots there, and they're operating. It appears like they're operating for the most part independently. So I guess I just wanted to hear more.
Yes. So it is true that currently there's this safety concern, and because of it, we don't usually see that many machines operating in the same workspace, which is a safety concern that would be lifted eventually if most of the machines do not have humans involved. The thing is that you may have this architecture currently going on with humans operating machine, and I would ask then how efficient it is. I mean, were you able to clear all your forests, and were you able to actually prevent wildfires from happening? The truth is that we have these measures in Portugal as well. The government sort of forces people to clean their lands, but the truth is that 99% of the land remains uncleared. So when I say that we need to redesign this multi-robot architecture, we need to redesign it even at the core. Even the processes that involve the humans in removing the vegetation, these processes need to be revised by lawmakers and other kind of organizations. And of course, then if we take a look at what we've been achieving in multi-robot systems in other domains like space exploration and things that are still in the paper, most of them, we understand that there are significant advantages in having somehow simpler solutions to solve very complex problems. And there are especially advantages in the domain of perception, because this different kind of, we know that perception is a huge thing in forestry robotics, as it is in many other domains. And we know, again, on a theoretical level, on the paper, that this collaborative perception is something that provides us an entirely different perspective of the scenario of where we need to operate. And I think this cannot be replaced by simply increasing the number of sensors that we have in a single machine. It is improved by simply distributing these machines in the field. And then it's all a matter of scale. I mean, if we have a robot that we know that can clear 1 hectare of land, then we know that if we have 10 robots, we're not going to be able to clear 10 hectares. We're going to be able to clear way more hectares through collaboration. Again, most of it due to the fact that we're going to improve the perception of the system.
I think it's worth recognizing, it was pointed out, there's also 2 very different applications between harvest and fuel management. And so I think the multi-robot case is very persuasive for the fuel management side.
Yeah.
Maybe not.
I guess this points out also the local legislation and the geography plays a lot in terms of the problems. Like for instance, as far as I'm concerned, fuel management is not a problem in Quebec. When a forest catches fire, you control it a little bit, otherwise you let it burn because it's it's so big. As long as there's not threatening houses, so it's not a big issue for us. And also I think the type of fuel that we have on the story is not so bad. Or the way you cut wood that changes from legislation to a legislation. So I think this is also, there's not going to be a one size fits all. Like I think self-driving cars, the roads are similar. The driving codes are different from place to place. But I think forestry industry is very tied culturally, but also geographically and biology to whatever you have in each location. I'm sorry, please go ahead.
No, I just wanted to add something in terms of fuel management. I know that you people are looking pretty much at the prevention aspect of it because we've been talking about it. But let's also take a look at the firefighting scene, right? I mean, one of the ways to try to contain a fire is through fuel breaks or fire breaks, right? Where we need to remove a certain region of the vegetation to avoid that the fire spreads. So again, I believe everyone can agree that a multi-robot system has an advantage, special distribution. So we can create those fire breaks, those fuel breaks way more efficiently if we are distributed in space. So again, as George said, it depends on the application. Some applications are very obvious that multi-robot systems is the way to go. Maybe some others are not that obvious.
It's also probably also worth calling out from the forestry side of things. Forest fires are not always actually a bad thing. And that might sound a bit weird, but forests are chaotic and crazy things. The time spans that we're talking about are much longer than often our lifetime. So they evolve dramatically over time. And forest fires are often one of the mechanisms for them to be a bit more dynamic and give new species opportunities. We don't like them because they emit carbon and because they light our houses on fire and kill us. So it's definitely something for us to manage. But there's also, for example, the other half of controlled burns, right, where we actually do light forest on fire ourselves in scenarios where it doesn't actually spread more and it actually de-risks future forest fire. So when you hear a forest fire in the future, don't always think that it's like an evil thing. It's just something for us to manage. I think is how I talk about it.
Yeah. I mean, some 3 species, like the seeds will only come out of if there's a fire. The trees, they're built actually for fires, to survive the fires and actually to start reproducing.
Which is so cool.
It is so cool.
All right, so we have a question from the chat, apparently. We're going to see if we can make the technology work for that. Here we go.
Hi there. Can you hear me?
Yes, we can hear you. Victor.
Okay, right. So it's not as much a question. I'm thinking about complementing a bit of what Mikhail was saying. In fact, we work together, so he'll know what I'm talking about. So there was something that was mentioned this morning concerning the fact that having smaller robots allows for a lot more flexibility in terms of operation, and having the ability to have multiple robots and small robots at the same time, which is something that is parallel to what we have in agriculture, for example, where people are trying to reduce the amount of soil compaction by introducing smaller robots. I think can also be a good pro for having multiple robots in operation. So yeah, just to add to the discussion there. Thanks.
Thank you.
Yeah, so if I go to the next question on my list, this is a very technical question. I'll target it at Philippe, but of course, I'd like to hear from everyone. If these things are going to dwell in a canopy, under the canopy in a forest, The SLAM solution is very important. We heard a lot about kind of mapping and perception. My favorite loop closure method is bag of words, visual bag of words, which we have had pretty poor luck with. So I wonder if you can shed some light on what the right way to do that is.
Well, I don't know the right way. Sorry, but I mean, there's loop closure and there's loop closure. There's also the time scale. Is it? I haven't been here. Have I been here 5 minutes ago or 5 months ago? And because there's several phenomena in the forest. Is first of all, there's the seasons. Like is the foliage going down? Are we gonna have like 5 meters of snow? So that makes because if you have a lot of snow, like your algorithm looks like the ground is going up, but your trees are sinking. So there's all these problems of the season change. So vision tends to be, as we know, heavily affected by the season illuminations, rains, etc., etc. So the long term, you probably want to go through semantic stuff, even like LiDAR. Like LiDAR is more robust, but if the foliage goes down, then LiDAR would be affected by that. Or like I mentioned, the ground going up. So I think combination of LiDAR and semantic, the semantic knowledge, what changes with the seasons. You could technically recognize a tree from its bark. Like we've done a paper where we use bark as a fingerprint. Interesting. You can actually recognize an individual tree. I would not recommend that for a SLAM system. That would be very expensive, but it is possible because the bark is quite unique from one tree to the other. But other things, again, thinking outside of the box, like the canopy, maybe you can have cameras that point upward. And again, the branches are unique pattern from trees to trees. And these branches tend to be quite stable over time. So maybe you can use overhead cameras to use that as a fingerprint. But it's definitely challenging. And I will maybe here to throw a bit of not controversy, but do we really need loop closure? Yes, for mapping, but let's not forget we're going to harvest those trees on my side because I don't do field management. So I'm going to remove those trees. So the trees will become a stump. So again, semantic information might be useful. But also if I clear the trees, the GPS becomes very nice. So that's the other thing, don't forget, the problem might solve itself, if the goal of my robot is to localize, step one is I'll cut the trees, right? And I'll get a tree harvester for free from that optimization process. So that's what I'm going to say for the loop closure.
I have nothing to add. I'm taking notes actually.
Okay, so if I can add, of course, that would work for your application.
Yes.
For field management, it would not. I just want to add to that technology, again, will have a very important role here. And picking on what my colleague said a while ago, the price of technology will definitely change. We've been seeing that on LiDARs. Currently, they are interesting radar solutions available in the market, and we're starting to see those below the 20K threshold. And radar technologies have the advantage of being able to penetrate a little bit more in the vegetation, which means that the landmarks will be more maintainable over time. Because even if there's some snow, even if the leaves are on the floor, we're going to be able to see beyond that, and that can be used a little bit more to improve loop closure. Having said that, is loop closure really needed? Well, for field management, it is, especially if we're talking about multi-robot systems, because they need to be working in the same workspace. They need to be in the same frame working. So yes, localization, I think, is inevitable and really necessary. The other thing that we need to invest, I guess, at the scientific level is on this spatial temporal representations. There are groups, very interesting groups all over the world dealing with that. We've been working with groups from Czech Technical University, for instance, where they deal with these spatial temporal models. So they're able, with a single camera, they're able to make a mobile robot navigate outdoors through a series of teach and repeat kind of routines, even when there are significant changes in the environment, when you have day and then you have night, or you don't have snow and then you have snow. So I think there's a lot of room in the technological level and in the scientific level to go over that. And I think it's going to be solvable. Yeah, definitely.
Actually, I think the only thing that I might add is that, again, because I'm curious if you guys agree with this, but it's a very homogeneous, right? And so if you're just thrown out into a map, I've heard a lot of our advisors even say, I always tell myself that's such a good tree. When I come back here, I'm gonna know where I am. I'm gonna recognize that tree, and it never works, right? Like even when they're out there, he's like, wait, where am I? And it's easy to get lost out there, even as a human. And this works pretty well. And so like it's so homogenous that I think getting a good initial guess is actually that much more critical to get a good placement. And initial guess often comes from GPS. Usually get a lock, at least in autonomous vehicles. That's how we usually do it. And here there's all those challenges, of canopy and whatnot. So I think it does actually present a very interesting element to this on initialization and making sure you have a good signal on GPS at some point before you start moving around.
But it's very challenging. We've been doing experiments in forestry, and from the moment we start with a few trees around, our GPS gets lost. So what happens is that our ecosystem sort of relies to some extent to GPS. So instead of improving what we currently have, we're making it worse. Of course, there are other approaches, and we've been discussing that with our colleagues from CMU that we're gonna try out. But I do believe that GPS is very important in many applications that we've been working on in the company. I think that it is not that important in forestry, at least for the kind of the domain that we've been working on.
Sure, interesting.
I'd like to jump on the bandwagon because you mentioned the word teach and repeat, which again, if you look at the problem, I guess I'm the harvester guy. So the harvester goes, cuts the tree, puts them on the ground, and then you have a forwarder that will go and pick up the logs. So if you look at this problem, this is an example of a teach and repeat. If you instrument the tree feller, which is driven by a human, then all the concept of or the problem of finding is they're going to traversable is solved by the harvester. The guy drives, picks up the log, you build a 3D map, you know where the log is, and then you upload the map to the forwarder. And the forwarder, all it has to do is follow the steps of the harvester, pick up the logs. So in some sense, there's instances where I believe the perceptual challenges are minimized just by the structure of the problem, the forestry industry. The other thing, which is not loop closure, is visual odometry. And I think one of the things that makes it difficult in the forest is, especially once you have all these branches on the ground, is visual odometry works great when the world is made of a flat surface, might be curved. But the understory of a forest is more of a volumetric thing. It's fluffy. And I think any method based on features or dense method will have troubles with fluffy 3D material because it's not what it's been designed for. So it's another aspect, I think, of what makes navigation difficult.
I've been trying to come up with a word to describe like that nature of canopies, and I'm just going to start using fluffy from now on.
That's very nice.
That's
Nico.
Did you have a question?
Just a comment. There was such a technology that we were hoping that would help us to solve some of this problem was GPR, ground penetrating radar, because things underneath are typically more stable over time, and they are a little bit unchanged by weather conditions or by seasons of the year. So the problem is that the technology is has promised a lot, but it doesn't reach a status that could lead us to use it. So we tried to buy one of those devices, and they are always saying on next semester. But if they manage to solve the technological part of it, I think it will be great for forestry, because it will allow us to map everything in a more stable way over time.
Yeah, we've been working with radar, not exactly that kind of technology. We've been trying some radar technology also, and we noticed that it definitely extracts way more features, and more than extracting features that are more static than cameras will ever do. It's meant for that. But as you're saying, if it's not available, then if it's not that the problem is the cost. We're still not there yet, but it's a matter of time. I mean.
GPR is actually another Greentown Labs company, so we should take note and talk to them. Thanks for that.
Yeah, so my next question is sort of related to the loop closure question, and it's one of representation. So, you have this world, it's a full 3D world, right? You can't approximate it as 2.5D really. It changes all the time. You also have a task that you want to accomplish within that world. And so there's probably information associated with the task, and there's been a lot of talk about semantics and things like that. So what do you think about sort of what are the good properties of a representation for this space? And I'll start with Mikhail.
Okay, yeah, so multi-layer representations are not new. I mean, there are many works in, again, intelligent transportation systems. We can have a layer that represents the physical properties of the scenario, another layer that represents the flow of humans moving around or vehicles and so on and so forth. In forestry, it's not that different. I mean, for instance, if we take again as an example our application where we want to remove vegetation, undesired vegetation, we may have a layer that represents the occupancy of the scenario, another layer that represents the vegetation that we want to remove, and so far so good. I think that the question, however, could be subdivided into different dimensions. One of them is what you said about being a full 3D scenario, and that we should not try to approximate. Well, but the thing is that we do it, and even in other 3D scenarios, we often do that for UGVs, and most of the time it is enough. So we pick on a 3D scenario, we represent it as an occupancy 2D grid, and it works. Of course, that it will depend on the application. I mean, if you have a machine that it's supposed to remove ground vegetation, maybe having a 3D representation will not be needed in the end. Maybe a 2.5D representation where you have a grid map or something like that that represents the density of vegetation could be enough for a UGV. It's not like the UGV will fly away and try to remove the vegetation from the tree canopy, right? If you have a UAV, however, I mean, yeah, if you want to navigate under the canopy, you need to have a full 3D representation, and we've been doing that. With octrees, for instance, which is one of the standards used by the ROS community for 3D navigation and 3D representation of maps. And it works great. It's very efficient. And efficiency, I mean, not only efficiency in terms of processing, which is important for the robot as an individual, but also efficiency in terms of communication. Because again, as we're dealing with multi-robot system, and even if we are not, we're still dealing with a system that requires a human in the loop, whether we want it or not, then we need to be able to communicate that map very efficiently to other peers. And octrees are great for that. But the other point of the question is, how are we gonna actually build this information? That's where all the sensing part comes in. I mean, currently we are using occupancy grids for navigation of the UGV. And because we're not yet dealing with the autonomous mulching of branches, we're only dealing with the ground. So far, so good, I would say. But we are talking about a Core A7, 32 gigabytes of memory, GeForce 2060 RTX. I mean, it's not great, but it's a machine that you would be able to play most recent video games with it. And still, most of the time, we have 100% occupied in all the cores, and even some megabytes of the GPU occupied. And yes, we're using, of course, we're doing a lot of things. We're using occupancy grids, it's a fact, but we generate those based on an octree representation to start with. We just make it simple, we flatten the scenario because for navigation, it's simply easier. But then we have our global planner, which uses the typical A-star. Then we have a local planner, which uses time elastic bands. Then we have a SLAM going on, which in this case, we're using a graph SLAM approach. So we're using already a lot of things, and we are already reaching the bottleneck of what the machine can do. So now imagine having to deal with all that in 3D. I mean, okay, of course that the machines will get better over time as the sensors do. It's a technological kind of thing, but most of the time what happens is that these machines are getting better, not for robotics. They are getting better for a specific purpose. Most of the time, again, it's video games. So they get better in terms of GPU processing, they get faster, but they are not concerned about whether they consume 100 watts or 200 watts, okay? In our case, sometimes we have only the CPU part consuming 100 watts, CPU plus GPU. So it's already a lot. Of course, that our machine is hybrid in a way because it's diesel and it's battery operated. So traction is all diesel powered, and the sensing part and the CPU and so on, of course, that has a battery. But what happens is that we cannot have an autonomy bigger than 4 hours currently, right now, and using this diesel and hybrid battery operated. So now imagine that you do this with electric vehicles, because it is the direction to go. No one wants to have diesel autonomous robots in the forest. I think it's not the way to go. Of course, right now it's how we do things, but there are many companies worldwide developing mulchers and other machines 100% electric, including some of those in Europe. Even Bobcat, I mean, recently called the Dozen or whatever, they bought the company. They're buying everything. And this, they showed, they made a nice exhibition of their first electric machine in December last year. And there are other companies like that. And we know that this is the direction to go. But again, we're facing a problem, because these machines, they have pretty much around 4 to 6 hours of autonomy. If we're gonna add all this burden, this intelligence on top, and it's an intelligence that requires a lot of processing, especially because of perception again, because most of the time we use deep learning, and deep learning is very power consuming. So what happens is that we're reducing by half the autonomy of the robot. Of course, we may argue, okay, technology will evolve as batteries will evolve. Yeah, but we're not there yet, and we cannot wait for this to happen. Maybe we need to look at alternatives, even in terms of perception. Everyone is very fixated in deep learning. Maybe we could take a look into alternatives. For instance, spiking neural networks have been proved to be quite cool. Many groups worldwide have been using them. We are working with one from IFRRIA University and also from Brazil. And they are using spiking neural networks to build a model of the Parkinson disease, so that they can study it a little bit better. And these spiking neural networks sort of like mimic how the brain really works. So it's not like the standard models that we're using of neural networks. And one thing that they have proved is that actually they can reach similar results that we reach with traditional deep learning approaches, with way less power needed. So I think that yes, technology will solve most of the problems, but we need to also be able to look in different directions, because I think there are different directions than the ones that we are currently employing.
So if I was to circle that back to the original question, all right, you recommend towards simplifying the 2D when possible.
When possible, for navigation, it does simplify our life quite a lot. But again, it's not going to work on every scenario.
Yeah. So what's an example of can you draw?
Yeah. An example of a scenario where it would not work, where you have, for instance, a scenario where you need to move in different layers. Let's say a bridge kind of environment, right? And you need to move on top and eventually remove vegetation, or a cave, for instance. And then you need to go below, and you need to also clean up this area. So this is a scenario, a physical scenario, where it's not possible to represent in 2D or 2.5D, where you need a full 3D representation. And we have those 3D representations working well. In UAVs, you have a lot of frameworks available out there, Move It and Octomap Planner and so on and so forth. And they work great, but they are not meant for UGVs right now. However, again, we should take a look around and see what other people are doing. First, in the game industry, we do have frameworks to deal with the Octree-based navigation. In video games. So we have planners that work on top of Octrees, both for UGV, not UGVs, but ground virtual agents and flying virtual agents, and they work really great. I mean, of course, there are many differences. There's a gap between robotics and video games, and it's up to us to try to build the bridge to pave this path. But I think that we should really take a look into what the game industry is doing, because in certain topics they are a little bit ahead of us.
Do you guys have anything to add?
I might try to be controversial here.
Sure, go for it. That's why we're here.
I'm sure all of you have walked in a forest at least once in your lifetime. And how many of you have built a 3D model of a forest? So, but you clearly all survived. You all came out of the forest. So I'm not making a claim here that 3D mapping is not necessary. But there is something to say that as humans, we don't do that. Operators don't build a 3D map. They just go around, get a field, cut the trees. There might be several reasons for that. I mean, we're good at topology, but I think one of the problem with topology in forests is you don't have a clear definition of what is a node. Like we do a lot of 3D mappings in buildings where a node, is a room. For high definition self-driving cars, I suppose you also topology, roads, corners, this and that. So it's clear, but forest, it's homogeneous thing. So it's hard to say, I'm going to build a topological map of a forest, and each node there's a tree. But there's something to say that humans don't build 3D maps of the forest, and that and it as 3D maps are expensive to maintain. In a way, building, especially if it's a metric map, it's saying, right now my decisions depend on where is the FL tower located, in comparison with me, or where is my bed. I mean, these are, things are far away, they don't matter. All that matters is what's around me, and I don't care where the FL tower is. So when you maintain a complete 3D map of your forest, that's what you're trying to maintain, is the distance between each tree, and it's very important. So I might say that maybe, again, we as roboticists, we're used to, we want to publish, we need to have metrics. Maps are a good way to measure things. That's where we came. So we'll try to use those tools to build, forestry equipment. So I'm not saying it's a bad idea. What I'm saying is it's what we used to do, but partially maybe it's due to the fact that it's where we came from, that we want to build a 3D map, and then so we're going to do planning after that. But I'm not necessarily saying that we should go back to the days of reactive, run the books. I think reactive systems where the world is the best model, and I don't need a map, and I'll just react, feel the trees and cut them, or clear the fuel. But I'm just saying, we have to think about, do we really need a 3D map, a thorough 3D map to do the job we want to achieve?
Yeah, but we need to be careful with something, and this is something that we tend to do, which is we humans do not need, and robots do not need. We are very different embodied agents in the first place. If, for instance, we want to use drones to help the ground robots because they have a very different perspective, they can retrieve way more richer information if they're able to fly under the cope. But to be able to fly under the cope, you need to have some sort of 3D representation in drones. So maybe not in UGVs all the time, but let's take a look first. If we have an UGV and we want to somehow clean a tree, so even if we don't have a 3D representation of the whole map, maybe at the local level, we need some sort of local 3D representation. So I agree with you. I mean, it's controversial. I believe that for navigation, for UGVs, a cost map will be more than enough in 100%, almost 100% of the situations. For operating, however, and if we aim at heterogeneous multi-robot systems, maybe we need something a little bit more than that.
Do you have any thoughts about planes and cylinders? Does that get us anywhere close to a representation? You model the ground as a plane and trees as cylinders, and you throw away a lot of
a geometric kind of.
Victoria Park in Sydney.
Yeah, right.
That's a great place to do it. Anywhere else, the trees are, just as simple as that. Sometimes trees, the head is,
Falls off
and it grows, it'll be a Y. So it's not even a cylinder. So your cylinder matching thing will return you either two trees or one huge tree, because it's going to try to match the Y, or the trees are growing crooked, or they, like Canadian Shield is like, it's we have 1 million lakes. Why? Because it's like this. So the plane assumption is not so great, and the cylinder assumption is not so great either, with all the branches you have. So it's unless you maintain your forest, which again is part of the geography. Some countries, I think it's in Sweden, they go and clean their forests once in a while. Back home, we don't. It's too big. It's just you get what you get.
And I think it could depend on your objective too, right? Like if you're just trying to navigate below and you just care about the trunk up until the first branching, maybe that's useful information, and you can abstract it away as cylinders. We tried to get pretty far on that and start hitting some, but I think if you start really getting into the weeds about trying to get measurements and inventories on trees for forestry, when they're trying to use it for timber, it's actually multiple different products within a single tree. And so up until first branching, as soon as you have a branch, you have nuts, right? And so it's a lower quality. You can use it in totally different products. Also with a totally different carbon footprint, by the way, because we care about that. But point being, there's a natural tapering to a tree, and you're trying to get volumetric measurements along it. If you start making that abstraction all the way down, and say it's a perfect cylinder, you start losing a lot of that measurement that they actually care about of how much of these different products are in this tree. You have to kind of respect the tapering and more detailed representations of that tree.
Yeah, that's why this multi-layer representation is a thing, because for navigation you need something, for operation you need something else. So yeah, I think that's the direction to take. Yeah.
Actually, that might be a kind of an interesting point to, if you'll forgive me, it's a little bit of a detour, but I think it's a super rich and a little bit of a holy grail in a lot of parts of forestry along these different kinds of representations. It's not 3D versus 2D, but these different modalities within forestry. Right? And so like we specifically think about, so I'm used to, again, autonomous vehicles. That's like, okay, we have radar, we have LiDAR, we have camera. These are the different worlds that we live in. In this space, we actually, at least at Gaia, we talk about it as below canopy, above canopy, and then satellite. And whatever you're using immediately above or immediately below the canopy, it's a totally different kind of data set. And so like the data association problem here is really fun and is really challenging. But like this almost is like the bigger problem that I think we have to navigate as roboticists, is how do we combine these different modalities that have insanely different big strengths and very big weaknesses, right? Satellite is often seen as a holy grail in forestry for good reason. Everyone holds it as this giant hammer and it's like everything's now a nail, but satellite, the reason they do that is because it's so scalable. It's basically free. It's so accessible. Right? Give me a bunch of engineers that I don't care the school. Give me, some undergrads. Give me a month, and we can crank out a neural net that trains on that data. Right? It's so accessible these days, but it's the worst measurement. Right? It's point blank because your sensor is miles away from the observation. Right? And so as soon as you get in the weeds, you're getting a richer measurement. And guess what? It scales like crap compared to satellite. Right? And so it's all about how do you combine these different. It's the same game as an autonomous vehicle. It's a very different world, but same game. How do you use these different modalities and their big strengths to overcompensate for the other's weaknesses? How do we scale the finer resolution using satellite to the broader scale? Sorry, a bit of a detour, but kind of an interesting.
No, that's fine. So I'm gonna go ahead.
Yeah, and to jump back on the mapping and loop closure and this and that, and so it's like when you have snow, you basically lose a lot of the ground texture, and it's like your robots will become lost because it's like nothing will work, right? Either the cameras will have the wrong exposure, or there's not enough features to trigger anything. So it's your robot will fail. But there's something interesting about driving in snow is you leave a track behind you. So in a sense, it's like here's your mapping process. Here's my trajectory. All I have to do is look back and I see where I've been. So if I want to do teach and repeat, all I have to do is you go back in my tracks that I just laid down. So it's it's simple, but it's different.
It's an interesting idea.
You talk about changing environment in this space, which is pretty unique. You can talk about leaf on and leaf off, right? It's totally different domains depending on which half of the year you visit the forest in. Yeah.
So it's been very interesting. I have one last question that I want to ask, just sort of broadly, and there's going to be some discussion about this in the afternoon, I'm sure. And we touched on it a little bit this morning. So we live in this world where deep neural networks are the thing, right? Those video gamers, they gave us all these affordable GPUs, and now we're doing everything with deep networks. Of course, that's very data driven, and especially in forestry, like labeling data is very difficult. And like Philippe says this morning, that 200 images is a good place to start, and then you double that and you get a 3% increase in improvement, and that just like, you start adding those numbers up, you're like, geez. So what do we do about this? Like, if we want to be able to detect features in these difficult environments and, figure out, label things, size things, the kinds of things we're talking about doing, how do we get over this data labeling bottleneck? And I'll just throw it out there to whoever wants to speak up first. And
do you mind if I jump in?
Go ahead.
This is what we built our business around. So I love this question. But this is actually a business answer to a technical question. So forgive me, but I see this as a platform question, right? And there's a cliche on platform of the chicken and egg problems. How do you, when there's a big demand for something, but then how do you get that something, right? Right now, it's very obvious. Everyone is so keen for data on this side of the fence, right? But the people on the other side of the fence, there's actually people going out collecting like huge amounts of data every day within forest, but they have no incentive to plug it into this, and there's no existing. And so the whole point is to really scale this. The current paradigm that you see with tech companies, which is silly and is hard to scale, is going up to them and doing this, right? And saying, hey, please, either let's be buddy partners, or maybe I'll pay you. It's hard to scale that relationship. If instead we find out ways to create value for the foresters while they collect data for us, right? Imagine people paying you to collect data for you and to label that data and to quality control it for you. That's what we're building up Gaia around, right? Is let's create enough incentive and enough value on the other side of the fence, and actually going to them and saying, hey, what are your pain points? How do we solve your problems with collecting data? Great, now here's a way to scale that. By the way, like here's this whole insane value that it's creating as a data platform, and then to connect that on the other end with all the people who can create some awesome value with it. And so I think that has to be the right answer here, is you need to create the right incentive and the right value on the other side of that fence to the foresters who are actually out there in the woods collecting this data. And then you need to find the right mechanism, the right incentive structure to start connecting that to everyone on the other side, and have everyone, all stakeholders have a win-win.
If I can add something to that, you mentioned collecting data, and that's definitely a big part of the problem. With us in robotics, it's not only about collecting data, it's also about somehow making this data useful in a way, so we need to label it. And this is one of the biggest issues we face in perception. We've been talking about semantic perception for a while in the morning. And we had this experience of trying to have an end user highly involved in our project to label data. So we're talking about RGB images, even with the near infrared band and everything, something cool. So, and they took months to label a few dozens of images. So because we need to segment to pixel level, this takes a lot of time. Of course, there are other alternatives to pixel labeling, naturally, more efficient a little bit, but it still requires a huge manpower to label the necessary amount of data needed by most deep learning approaches. So I think there, regarding this question, I think that's where, again, video game technology can help us a little bit, because we're reaching a point right now in video game technology where we have photorealistic scenarios that are really amazing. I mean, if you Google or you go on YouTube and you put Unreal Engine 5 and you put, for instance, train station, you're gonna see one of the best amazing scenarios of a train station from Japan that you can not distinguish it from reality, and it's generated. Okay, if you look for forestry, again, Unreal Engine 5, you're going to see a forest with a high level of detail, of lightning, of smoke, even of a wildfire going on. So this data has a very interesting advantage over real data, which is the fact that it's labeled by default. So everything that you acquire, that you don't have to go to do any post-processing. That's the good part of it. What's the downside? It's that if it's not representative enough, then you may be tweaking your method, as presented by David in the morning. But I think that this is again the direction that we should be looking at. So that's my 5 cents to this. Yeah.
I'm gonna jump in. Labels. Do we need them?
I like your thinking, positioning, cut down the trees.
All right, let's cut down the trees.
Labels, do we need them?
Do we need them? So again, where we came from was ImageNet, right? Half a megapixel pictures of cat with a bounding box. This is where we came from. And I think right now there's a big push to get rid of labels, hand labeling, through these self-supervised or semi-supervised techniques. And I'm a big sensor guy. I love sensors. And why don't we let the sensors do part of the job for us? Okay. So let's instrument to death harvesters. Okay. And when I say to death is gigapixel cameras, hyperspectral cameras, LiDARs, and what have you not. Okay. And then play these games, like these pretext tasks that are used for self-trainings. For instance, to segment it, if I give you 1 pixel and I tell you, is that bark or not? It's hard, right? Because it's brown, but it could be dirt. But if now I zoom in and that becomes a 64 by 64 pixel patch, it's much easier to say, okay, this is bark. Well, this is what the gigapixel image gives you. So you collect those gigapixels, you basically train a classifier for textures, and then you zoom out, and then it says, no, this is my label. So it's not perfect, yes, but it gives you all this pre-training, which is very expensive. Same thing, you have hyperspectral. Hyperspectral will give you a little bit of information about the physical composition of the material. So you just train, he says, no, here's an RGB image, predict me the hyperspectral. So I think you have a CAN bus sniffer, so you have all the commands of the operator. From the video streams, predict me the CAN bus commands. They'll give you an idea, or from a picture, predict me what's going to be the next CAN bus, or where we're going to be the head. So there's a lot of information that we're not using right now that I think we should be thinking about. Let's not make the same mistakes as ImageNet. Let's enjoy all these sensors. Let's collect a lot of data, and let's try to squeeze as much as we can, so we can leapfrog the fact that we don't have ImageNet for forestry. So that would be my take.
All right, well, thank you, panelists. Fantastic discussion. So let's give them all a round of applause.